Hello everyone, reporting today for First Updates Now, I'm Abbas, and with me here is none other than Team 12993, RoboKings Aurum, all the way from Australia. They have had an absolutely fantastic season this year. They ended second after all the qualifications happened in the Ochoa division, some very tough matches, and then were picked by the first alliance in Row 2D2, going all the way to championship finals where they ended as the Finalist Alliance first pick after just some incredible matches. I can say with full confidence that this is going to be one of the most mechanically impressive behind the bots and robots that almost all of you FTC viewers will ever see. I am just so excited to jump into it. All coming up on Behind the Bot.
This video on fun is brought to you by viewers like you and also in partnership with the following. The new Robot system by AnyMark can reduce complexity and enable robust builds. Parts aligned to a common 1/2 inch grid, simplifying construction and allowing alignment of both structure and motion components. Robots enables teams to always have the parts they need to complete a build. Head on over to anymark.com/robots to learn more and order today. Support Fun's content creators when you sign up for a membership on YouTube Join. You'll get access to special perks like emotes, loyalty badges, and Fun members will even get early access to our scheduled videos and more. 100% of this revenue will go back to our correspondents to help recognize their efforts. Click the join button in any YouTube video to pledge your support.
Okay, so I guess Tintin and Tinko, my first question for you is, after Australia Nationals, you already had a very competitive robot. What drove the decision to build just this absolutely beautiful machine?
Well, most of it is just obviously a love for the competition. Like, we want to try and push, like, one of our season goals when we started the season was to try and push, like, the limits of what's possible in FTC. I mean, we have, like, a battery that powers everything, so we can only do so much, but we really just enjoyed the whole, like, iterating process. So I guess we thought we can do better than this. There's better designs out there. There's more things we can do.
Yeah.
So, and it paid off last season in power play, so
why not do it again? Yeah, great. So now talking a little bit just about the overall architecture of the robot. You know, we've seen a lot of teams with the intake, extension, extendo, all of that stuff. What drove the decision to have the horizontal extension on the deposit and all of the degrees of freedom?
So after Nats, we had the pitching slides and the intake, which was virtually remained the same. We chose to add this because with the pitching slides, it made depositing the yellow pixel much easier and also allowed our autonomous like max points to be much like greater. So we can deposit like fully out of the side here, which means we don't have to change our heading, which means we keep relatively a static heading in auto, which is better for consistency, like and speed as well. And we can also place out of the way. So
fantastic. So now we'll start with the intake and then end up all the way at the deposit. Over here, why don't you just walk us through the general design and then we'll jump into the specifics.
So we use an active intake for our intake. We have a bottom counter roller made out of silicon on a carbon fiber tube, and it's all run by one bare motor on the bottom. We've chopped the encoder off to reduce the weight and make it really light. So we have our bare motor runs with GT2 2mm belts to a gear here on an axle where we have 2 gears which help reverse the direction of the intake motor for the bottom roller and the top rollers. Once we intake pixels into our chute, our top pixel, which we use this for our yellow, we have a one-way gate made out of polycarb that's compliant, so pixels can't fall out. We have a chute that comes up and a linkage, and it over-centers when it's up. When our transfer comes down and tries to pick up the pixels, we have these polycarb flaps which are sprung out, so it's a passive release into the core, and then our chute comes back down.
Yeah, I mean, there's just so much going on here. Definitely take a really in-depth review to get through, you know, just the weeds of it. But one thing I want to focus on first is the carbon fiber. I think we've seen carbon fiber become more and more popular, but something to this extent is I don't think we've really seen by many other robots. Was it just purely a weight decision, or was there something else behind it?
yeah, so carbon fiber is roughly 40% of the weight of aluminium, and it's also more rigid as well. Because we were adding more slides, we were adding another like degree of freedom and more weight. We still want it to be really, really fast on the field. And the way to do that obviously is decrease the weight, therefore you have greater acceleration.
Yeah.
So carbon fiber was one of the things that we did to decrease the weight. And we actually designed our intake and deposit in 2mm aluminium first because we knew, you know, carbon fiber would be the end game for the robot. So if you, well, earlier in the season we had this thing built in pocketed 2mm aluminium, which actually held up surprisingly well. But we knew when we did a rebuild for carbon fiber, we could do that second rebuild with all our flaws and issues fixed.
Yeah.
With the weight advantages.
Yeah, and you mentioned about iterating and how much you guys love and going through that engineering design process and fixing things. Now, with all of these one-way gates and latches and ensuring the consistency of the robot, was that done through iteration? Was that done through CAD and simulation? How did you guys make sure that it worked every single time?
Yeah, so consistency comes from all of that. So you can design a consistent mechanism, you can design an inconsistent mechanism. Admittedly, this is probably on the latter side, but also you can make a complex mechanism such as this consistent through tuning and optimization. So, like, as you can imagine, we've had many issues with the intake, like jamming, holding these in, finding a solution for this. Like, even if you watch the finals that we just had, like, you just saw a pixel got stuck in here in one of our intake. So even now, World's finals still consistency issues, but through all of that, that's what we try and do through the whole process. We give it our best, I guess.
Yeah, and now talking a little bit about the programming behind all of this, I know the axons have that fourth wire and you guys want to ensure that consistency. Is that something you're using throughout the intake, or really is it just relying on the timing and you've just tuned that as much as possible?
We don't use the axon fourth wire on the intake, but it's just mostly timing. So we've done a lot of testing, and there's also other sensors that we use too. So like a standard 2-color sensor setup from underneath, and we have a limit switch here. It might be a bit hard to see, but from here, it's right there, and this piece is compliant like that, so that when the chute goes up like that, it will flick the limit switch, and we know when the chute's up, so we can have a transfer, anywhere.
Instantly, pretty much. Yeah.
And same with these, we also added these are other sensors that when we hit the wall, it knows when we hit the wall.
That's fantastic, yeah. Now, talking about when the intake comes into the robot, I know the transfer is not just as simple as it is on other robots. You've done a lot of little things here and there to ensure the consistency. So why don't we bring the intake in, and as we do that, you can talk through all the different ways you've improved the consistency and speed of your intake and your transfer.
Well, we wanted our transfer to be as fast as possible. So we didn't want to have repeated movements, such as coming down and grabbing the pixels and coming back up. So we knew we wanted to meet at a vertical point. In our robot, when the intake comes up, the pixels get pushed, the hole in the pixels gets pushed into the tab in the claw, and the pixels get sprung into the claw. When our claw powers on, we push these linkages down, and it pushes apart the two compliant flaps, so the pixels can't come out. And then we pull out the outtake, and because the polycarb flaps are strong, the pixels go into the outtake.
I see, and correct me if I'm wrong, but you guys also have some sort of locks to ensure the intake slide is at the correct position every time, or is it something else?
Yeah, so we use a micro servo. If we pull the slides in fully, we use a micro servo with an over-the-center linkage, and when our intake slides it in, we center it over the standoff. We do that so we can turn off our bare motor, which powers our intake slides, and know that our slides aren't going to come out, so it helps with battery.
So for weight as well, on top of the carbon fiber that we did, one of the other optimizations was having bare motors for everything that we basically could. So 4 of our mechanism drivetrain wheels are powered by bare motors, and it's a 2-stage reduction. That saves, so it's basically 7 gearboxes that we're saving. It's roughly 1.5 kilograms reduced just from doing that.
Yeah.
And also makes the packaging easier. And because we, like Tinko mentioned, we only run our intake slides off 1 motor, it needs to be extremely light for us to not have power draw issues, number 1, but number 2, be fast enough for us to cycle really fast.
100%.
So that's the decision behind the bare motors.
And now talking just from an actuator's perspective, so you said 7 out of 8, so you have 8 motors you're using, and then from the servos all 12, something else?
So yeah, we're at the motor and the servo limit for what we're doing. So you'll see maybe when we talk about the climb, like how we've had to work around
compromise.
Yeah, and just from a battery perspective, how does that work out?
Okay, so there's a lot to talk about here because you're really pushing the limits of what like an FTC battery can do.
Yeah.
We've done a lot of optimization on like the battery draw and power usage. But we typically run 3 matches before we have to change battery, which is pretty good, and it's like a standard kind of robot.
Sure. Yeah. Now, okay, what one of the just absolutely most insane mechanisms I think we've ever seen in FTC is just your entire deposit. So starting just with the linear slides, I know you already have a pitch degree of freedom on this. So let's start with that, and then we'll get through the rest of the deposit.
We've had our pitching degree of freedom since the very start of the season. We wanted to be able to have as much horizontal extension for fast cycles. So once our slides come out, we have 7 servos on our outtake. So we have heaps of degrees of freedom as well. We have our slides come out, our mini turret, which we have kinematics, which means that it automatically angles to the backdrop. We have our linear rail. We have an arm that goes up and down for our transfer, a pivot, and then also the claws. So,
yeah, that's just absolutely insane. Now, starting with the pitch degree of freedom, like on the base of your slides, yeah, how do you power it? I mean, there's just so many different ways to pitch slides. What have you found to be the most effective?
So we use a motor. This is the non-bear motor on our robot. We have a motor sitting in the drive base, and we have it. We gear it to an axle that goes across the middle of our robot. We read the position of the pitch with an axon encoder, and then from our pitch, we have a linkage which is attached to the axle. I think Tinzan will point it out.
Yeah. So the linkage sits here basically. We've done a lot of optimization to reduce the backlash in the system, which the axon encoder also really helps with because it's absolute and its position doesn't change across matches.
Yeah. And now going on to the next, I guess, your slides themselves. We've seen a lot of teams implement really fantastic slides. One thing I've definitely noticed with yours is the rubber bands and just stringing over here. Talk me through that.
It's a very common question. We get a lot of questions about the rubber bands, but basically, last season we did this as well, but it's how we counter spring our slides. So this side is fully cascade strung. So that means if we pull this string, the whole slides will be counter sprung up. So because there's like such a low mechanical advantage, we can pull this string really, really hard by adding a crap ton of rubber bands to an arm, and it works. So you can see like the slides will stay up at their correct height. What this also does is, and why we also prefer it over other counterspring methods, is it's non-linear. So you can actually adjust how much you want to counterspring at certain points. So what we found to be the best is that when we're further down, because most of the force is going into the joint, we don't counterspring our slides as much. So when we're having, we can transfer easier because the slides will come down. And then when we're extended, the slides hold their position much easier. So we're drawing less current, when our slides are out.
Yeah, that's really ingenious. And just from a sort of mechanical or material perspective, I guess, or I would say is obviously you guys know springs exist, act like real mechanical springs made out of metal. Why use the rubber bands instead of those?
Well, springs just straight up aren't strong enough.
Okay.
The force in these rubber bands is really, it's a lot.
Okay.
If we were to use springs, it would be
probably be a
extremely
safety
bulky.
hazard.
Yeah, it would be a safety hazard.
I see. Okay,
and
yeah.
we probably wouldn't be able to fit it in.
That makes sense. Now, going on to the arm slash end effector, I know first you said there's the pitch over here. Looks like it's an axon with just a very small linkage arm to it.
Yeah.
Okay, and
so
now...
this keeps level with this.
Okay.
We use kinematics for our whole life.
Okay. Got it. And now going on to the next part of it, I guess, would be your yaw degree of freedom. Walk us through the design behind that, anything you did to ensure it's very robust and won't break at all.
Yeah. The main thing we were considering, when we added this turret, we knew we wanted a rail and turret, but we needed this, other pitch degree of freedom so that the turret would stay parallel to the backdrop. So with this, we, like I said before, run inverse kinematics so that it stays exactly where it needs to, and we're always parallel. Yeah.
Yeah. And I see you guys also have some counter spring here. Or is that something else?
Yeah, that's just so if the servo powers off, we hold our position.
Okay, cool. Yeah, so now talking about the double Cascade Rail, why don't you just walk us through how it works very carefully, and then we'll jump into some more details.
So for weight, again, we have 2 layers of Gen 7 linear rails, and what we've done is we've actually cascade strung them on both sides. So from our outtake to this bearing to one side of our reel, which is powered by another axle servo, and then on the other side the same. So essentially when the reel turns, one side lets out slack for the rails to move in a certain direction, and the other side of the circle takes in the slack.
Okay, yeah. And just from like a build perspective and any issues you faced with backlash, slop, things like that, things you would expect from a mechanism, how did you deal with those?
This was probably we had the least issues with this.
Okay.
There's very little backlash with this. We've also got it set up so that it's basically 355 degrees, which is the max range of an axon. So one way to another. So we don't have to use an external encoder. We just do a normal set position, which that also helps with, like the update rate. So it's not gonna be off ever, really.
Yeah, that makes a ton of sense.
There isn't any backlash here, so you can kind of see.
Yeah, wow, that's just really incredible. And now going on then to the things all mounted to the rail, what's the first mechanism, and then,
So the first mechanism on our rail is our arm, which we use to bring out from our transfer over to the slides, over to the backdrop. And then on the arm, we have a pivot, which allows us to make mosaics really easily. If we have a color and a white, we can just switch it. We have all the degrees of freedom on here.
Wow, yeah. And just from like a design theory perspective, when determining the length of different mechanisms, like let's just take this arm, for example, was it more based on packaging and how you had to fit it in, or was it more based on like the forces and moments required from the servo, or something entirely different?
It's a lot of factors. So I'll use the example that you gave me, the arm. So first of all, the arm weight on our outtake was the number one priority because of all the servos and because of these rails. We knew we had to keep weight down if we wanted a competitive robot. The other thing, which obviously a shorter arm, smaller weight. The other thing is with the transfer, we're close to the 18 inches. So, and our intake has to come quite in to be like a working intake, basically. So that's how we basically had to balance those two constraints.
Yeah.
And the pivot point, like we tried to make that as far to the back of the robot as possible, but not too far back that everything is not contained within like our back little ramp plate here.
Sure.
But it is mainly, like for that example, mainly weight and packaging. Yeah.
Got it. Yeah. And now talking about a little bit of the other aspects of the robot, one thing I think that I want to circle back to is kind of the superstructure. With weight, that's one of the biggest priorities. How did you maintain rigidity throughout the robot, even though it's so light, or as light, given all of these mechanisms?
That's what the carbon fiber is for.
Okay. And as far as like cross beams and things like that go, again, just carbon fiber, or any other things you want to highlight?
In CAD, when we design the robot, we try and be like pretty smart about what's happening with the forces. Like for example, we only power, this is something we did last year as well, we only power one side of our intake slides.
Okay.
So we knew there was going to be a lot of force twisting the intake when we push it in and out.
Sure.
We have to do that because of our motor limit, but we can also add like extra cross bracing here, and we can stabilize with this ramp, like these two side plates. So we are smart, I guess, about where we add bracing. In the design too.
That makes a ton of sense. And now kind of closing out on these things, I know one thing you wanted to talk about was the hang mechanism and how you dealt with the actuators problem there. Take it away.
Well, our old Nationals robot, we had a very similar hang design. We had our hooks here, which released our hang, and then it sprung up and we actuated it with our pitch. This year, for our world spot, we wanted to add more degrees of freedom with the rail, so we had to sacrifice the servo there. What we've done is we actually have a passive release of our hang. In game, we only pitch up to a certain point. When we release our hang, we pitch up past the point, and we have wedges here, which push out these, so our hooks are actually just sprung in with more rubber bands.
And then obviously.
Wow. So you just hang using the pitch of your slides to retract the hooks themselves? Okay.
That's why we need the gearbox, because it needs to be a high torque motor.
I see. That makes a lot of sense. Now, I guess my final question from you guys is more from a strategy perspective. I mean, you guys have done incredibly well at Worlds, at all of your competitions for the past couple years. What advice do you have for teams looking to perform at a similar level from a strategy perspective?
Strategy, like, it's a very broad term, but I can answer the question on what I think. Like, FTC is a game of time, so the more time and energy you put into your robot, the better you'll get out generally. Like, that's really it for like 95% of the cases. Like, a lot of teams ask, like, how do you design or build a robot like that? And the answer I give usually is a lot of time. Like many hours iterating, CADing, coding, thinking about strategy. And then on the actual day, I guess things play out how they play out, and
Yeah, and I guess, yeah, that was really fantastic advice, I think, for everyone watching. And also from an eliminations perspective, how would you say your strategy shifted for those compared to qualification matches in Houston specifically?
Qualification matches are more about consistency. So, for example, in this game, things like shooting for zone 2 instead of zone 1, maybe lowering your auto or trying to work with partners better for consistency, especially because the skill cap is like not as high. It's different for every game as well. So last season there was a score cap, so it was different in that elimination matches it was more strategy based.
Yeah.
Whereas this one you can kind of go out and score as much as you can.
RoboKings, thank you guys so much. I mean, I think we could have probably spent 4 hours doing it behind the VOD, and there still would be more things to show on this robot, but hopefully everybody can take away just a little bit from this and improve their designs and their robots for years to come. So, RoboKings, again, thank you so much. Reporting for First Updates now, I'm Abbas, and this is Team 12993, RoboKings Aurum.
Thank you.
The new Robot system by AnyMark can reduce complexity and enable robust builds. Parts aligned to a common 1/2 inch grid, simplifying construction and allowing alignment of both structure and motion components. Robots enables teams to always have the parts they need to complete a build. Head on over to anymark.com/robots to learn more and order today.